Great. Well, first of all, thank you, everyone. And we'll open this talk with a quote that I found interesting. It says, all software is open source if you get good enough at reverse engineering. And while this is probably meant to be a joke, I do think there is some truth into this. This talk is a case study of reversing Apple's AUSampler audio unit plugin, and in particular, this piece of functionality that displays voice count. It will be divided in 3 parts. So we will first look at the problem, why we were doing all of this. We will then go through this process of finding this voice count implementation and using it in our own app. And finally, look at some interesting results that we were able to achieve. Okay, so let's talk about the problem. We've worked on this app that is basically a digital synthesizer for iOS, and the basic building block of this application is AUSampler. And AUSampler is audio unit plugin, so it can be loaded in a host app, but it can also be used via programmatic interface. So we can instantiate it here, we can load a preset to it, and we can use it, play some notes. And this preset this is the file where you describe your instrument, your audio samples, layers, zones, and so on. And the problem that we encountered was when, for particularly complex AU presets, complex instruments, we noticed that as user was playing these notes, at some point when a newly note is played, there would be no sound. And this led to this investigation process where we quickly realized that debugging this problem inside of the application was limiting. So what we did is we went back to AUSampler plugin, and primarily because it had this nice voice count metric that we could use to guide our debugging process. We also needed a host, so we used Apple's AU Lab for that. And then after a while, we had some results of this process, and the results were unfortunate. It was that AUSampler has a limit of 256 concurrently playing audio samples. So we had to work with this and design our instruments around this, but there were still some open questions. First, in the app, in our iOS app, we observed a different limit, which was unknown at that time. And the other is that our iOS app, uses multiple AUSampler instances. So we wanted to understand how it behaves under those circumstances. And this is really why I became interested if we can get this voice count metric implemented inside of our iOS app. And that is what led to this debugging journey that we are about to start. So first, what I did is look in documentation and official headers, but unfortunately, there was nothing there. So I made some kind of high-level plan. And the plan was, since AUSampler is really a black box for us, one thing that is exposed to us is UI, and we can start from there. So what we will do is we'll find a label that displays this voice count. We will add a breakpoint to when this label is being updated. And then we'll navigate the stack trace and hopefully find something in that stack trace that might be of interest to us. So let's get started. First, we need to open our host and attach debugger to it. And if we do this, this will fail because AU Lab doesn't have debugging entitlement that are required. But fortunately, it is fairly easy to work around that by resigning it. So what we do here is we copy this application to another location and invoke code sign with my code signing identity here. And if we now repeat this process, we will get attached successfully. So we are in. Now, one thing that's important to mention at this point is that AUSampler is loaded in process with AU Lab. So by debugging AU Lab, we are debugging AUSampler as well. Okay, so we are in and we need to find our label now. But AU Lab is multi-window application, so we first need to find our window. And to do that, we'll use probably most common LDB command, PO, which will print object description. And the object that we'll start from is this shared application, which has this key window property. And if you run this, we'll get this inspector panel with its memory address. Now, we still don't know that if this is our window or not. So let's also get Windows title and we get instrument 1 AUSampler. So that's great. Now, to avoid this repetition, another way to run this is by using expression, and this expression on the right-hand side will be stored in this temporary variable that we can reuse across our debugging session. So we can PO $8 and get the same result. Okay, so we have our window now. We need to find our label now. And to help us with that, there are a couple of GitHub repositories that export Apple runtime headers, including private APIs. And the private API that we are interested in is this one, called sub-tree description. And if we invoke sub-tree description on our Windows content view, we will get this tree-like description of the whole view hierarchy. And now, with a little bit of search, we can find our label, which is actually an instance of NSText field with its memory address. So let's run a little experiment at this point. What we'll do is we'll run another expression that will try to update this label by calling setStringValue. And if we run this and then continue the process, this will indeed work, and our label will be updated to ADC25. So we have our label now, and since we are able to update our label by calling setStringValue, we can assume that AUSampler does that as well once the voice count changes. So we'll set the breakpoint to setStringValue, and after we continue the process and then play some notes so that voice count changes, AUSampler will indeed invoke setStringValue with the changed voice count, and we will be stopped in the debugger. So this is great. We remember our high-level plan. So we wanted to find label, we wanted to set the breakpoint, and now we want to investigate the stack trace and see if there is anything interesting that can help us in our own implementation. So let's do that. To print stack trace, we can run BT, which will print a bunch of frames, but there are a couple of them that are interesting to us. So what we can notice here is that NSFireTimer, presumably periodically, invokes this unnamed symbol. We'll get back to that. And unnamed symbol updates the label. So let's first visualize this. So we have timer, which is calling unnamed symbol, which does something to calculate this voice count, and it updates label after that. Let's first find out what unnamed symbol is. So what happens here is that LLDB, it understands that this is some kind of symbol, but it doesn't know which one is it. It's not public symbol. Fortunately, what can help us here is Objective-C runtime. And using our previous example, Objective-C is a dynamic language, and it uses a technique called message passing. And the basic format of message passing is the following. So we have a receiver, text field in this case. We have a message, and we have arguments. And what this gets translated to at runtime is something like this, where it's translated to Objective-C message send call with these three arguments. So we know that our unnamed symbol is invoked in this way with some of these arguments, so we need to somehow unpack them. And the answer on how to unpack them, how to find them, lies in something called calling convention. And calling convention is basically a contract between caller of the function and the function itself on how arguments are passed. This differs on architecture, but on my machine where I was doing this, so these first three arguments will be passed in these registers. And this is what we need to do to find our unnamed symbol. We need to look into X1 register when the function is called. So let's do that. We will first set a breakpoint to the entry point of unnamed symbol. This is important because at this point, registers will have these values. And once we get there, we need to print those values. So X0, we have sync performance view controller. And in X1, we have update periodic events, which is what our unnamed symbol is. OK, so this is what we have. Now let's find out what update periodic events does to calculate voice count. And to do that, we will disassemble it using DD. And what we will get is a bunch of assembly, but there are these branching instructions that are interesting to us. So we can think of them as a function calls, and we can assume that one of them calculates voice count and returns the result to update periodic events. Now, to find out which one, we'll use somewhat brute force approach here, and we'll just step through this code by stepping into these function calls, and we'll see where we end up. So after a couple of steps, we end up in another unnamed symbol. This time we know what we need to do. So we have AU arbitrator as a receiver, and we have num voices as a symbol function method. So our picture is getting more complete. Let's repeat this procedure for num voices. After stepping a couple more times, we end up in yet another unnamed symbol. And this time, it's sync UI utilities get integer property for AU. We have this now. Let's find out what get integer property for AU does. By disassembling it, what we get is, again, some assembly, and we also, again, get some branching instructions, but this time they are different. So they jump to another framework in this case, and call AudioUnit get property and AudioUnit get property info. And these are actually public functions. So our final call tree looks like this. And if you think about this, this is really the best we could hope for. The whole chain of these calls ends up with a call to a public function that we can call ourselves. So we first need to find out the values that we need to call them with, and most of these can be filled in in a straightforward manner, but one of them that is interesting is this ID, which identifies voice count parameter, what we are what we are asking AUSampler for. And we already know the answer on how to find it out. Since this is a function call and ID is the second parameter, we know it will be in X1 register. So let's do that. We will set a breakpoint just before AudioUnit get property is called, because remember, at that point, registers will have those values. Then after we get there, we will PO $x1 and we'll get this value of 4104. And this is really all we need to implement this in our own app. So we just extend AV AudioUnit and call AudioUnit get property, and the only interesting value here is this 4104, which identifies voice count. So this was fairly successful. We were able to implement this in our own app. We were able to see voice count and how it changes and answer the questions that led to this. And the results are even more unfortunate. On iOS, the limit is 128 concurrently playing audio samples. And this is global limit across all sampler instances in your app. So at least we knew what we are working with, and we could design our instruments so not to hit this limit. Now, encouraged by this success, I started wondering, AUSampler exposes a lot more of these properties in the UI. Can we find all of them? And the answer is yes, and the key piece of information is that all of these call AudioUnit set property when they are updated. So we just need to find these IDs. And still, it would be quite time-consuming to go through each of them one by one using this process. So I did a little bit of automation by using the framework called Fishhook by Facebook. And Fishhook allows you to rebind a public symbol from some binary with your own implementation. So what we will do is we'll create a little framework that rebinds AudioUnit set property with my set property. And my set property will just print these IDs that we are interested in. We will then inject this in AULab. And then hopefully once we start changing these values, our implementation will be called and these IDs will be printed in the console. So let's create this framework. So we first create this little Objective-C class called hookLoader, and in its load method, we call this rebind symbols, that is a function that Fishhook exposes to us, and we rebind AudioUnit set property with my set property. also providing a pointer to original, where the original function should go. My set property, as we said, just prints these values that it's called with, and it calls original set property, so that things keep working. And we inject this to the AULab by running AULab with this environment variable called dial-D insert libraries, which will basically tell dynamic loader to load our framework, the framework at this path, in our binary. Once we do this, we get our log, and once we start changing these values in the UI, we will indeed start getting more and more of these logs, which helps us to easily inspect these IDs and potentially some other parameters that we are interested in. So we pushed limits of AUSampler over the years. We've had a lot of fun with it, but also a lot of challenges. And as a result, we wrote these 3 blog posts. And the final blog post, which we call missing documentation, also has this table where we list all of these properties that we found with their associated IDs, data types, and AU preset paths. It is unfortunate that there is all of this functionality that is not documented by Apple, so we filed this as a radar to Apple along with many others. Some of them were fixed, some unfortunately not, but we were very happy that Apple fixed this limit in iOS 16 for us, and it's now 1024, concurrently playing audio samples, which really enabled some new use cases for our app we were looking for. To conclude this, this could be considered a successful reverse engineering, but I've had way more unsuccessful ones, and not everything is open source if you know reverse engineering, but you can learn a lot, and you can get lucky sometimes and find something. And with that, thank you for listening.